And the rest of them? Going back to figure scarsa. Eu não sou isso, ela só queria, ela foi, eu sei. Não, sério, você mudou minha química cerebral. Vai tudo, são. Vai para escolha, qualquer escola do BPF, qualquer coisa. Cara,
Maybe go ahead and you can again because I want to ask something to the people before you start. Just ask a question.
If I can write something.
Yeah, Milton, it's you. Ask the question.
Yeah, sure. I told everyone.
I think there's good 4 or 5 people that got.
Yeah. So I guess we can start, right?
So guys, I wanted to ask you a question, which is coming from a doubt that you had yesterday. So do you think the Dicke model at finite n or large n is a solvable model? By solvable, I mean you can analytically find spectral distance. So
To me, looks easy enough.
easy enough. What would you do? So guys, good morning. I was asking the question to the audience whether the Dicke model is a solvable model in the sense that you can analytically find its eigenenergies and eigenfrequencies. So its eigenenergies and its eigenvectors. That's what is solvable. I'm taking benefit of your question yesterday to ask the students if they think, I repeat it for the third time, if the Dicke model is analytically solvable or not. Final level.
Can you complete the spread on the diagram?
You want to complete this, you want to complete the square. So
Can you have a?
which term do you want to add?
I don't know, just write a further diagram X and then you have an harmonic oscillator with a independent.
It's a good start, but it will not help you. What's the problem of the Dicke model for you? So let's say if so sigma x is sigma plus plus sigma minus, right?
Yes.
So if this sigma plus and sigma minus were replaced by f and f dagger over Kelvin, or b and b dagger over Kelvin, will you be okay with it? So
It's just Jordan Wigner, the spins.
Jordan Wigner works only in 1D. You start
Okay,
with
yeah.
Jordan Wigner on this, you will get a gigantic string. Before you can get there.
Oh yeah, you have to have access to.
Right. So this guy is sigma plus sigma minus. Now I ask you, imagine whether instead of this you have first option f plus f dagger, where F of course are fermions, or you have B plus B dagger, where B are bosons. And of course, the point is that this is like the operator X, and this is like the operator X. So what I'm doing is that I'm trying to copy paste. So, and of course, you will do the same here, right? So this will be in the first case F dagger F, and in the second case B dagger B. So would the model of this type be solvable, the variant 1 or the variant 2? Or the spins are problematic for some reason?
Yeah, it spins A, and you can find like the eigen values for A and eigen A quite easily. And then those are space states. And then one of the spin operators, we can also make an eigenset of both. But get the big problem is that we can find an eigenset of both the spin operators at the same time. Otherwise, we just use that operator, that spin state multiplied by the space state of the A operators and have eigenset. Would be awesome.
Okay,
Can't do that.
let me simplify a little bit what you said. Focus on case number 2. If I have a model is A dagger A plus B dagger B plus coupling A plus A dagger times B plus B dagger, we'll be able to solve it or not?
So can you do a probability bond transform?
All right. So a problem of 2 bosons is always solvable by a rotation, right? It's called the probability bond transformation. So why can't I do it here? What's the issue with spins? What's wrong with that? Because spins are not bosons, right? What are they? Statistically.
Fermion. No,
That's the typical answer you will get if you were in my class in Mainz. I will make a sound. Weird, right? So no, they are not fermions, guys. What are spins?
The spins are cycle states.
So spins on different sides, polymetrics on different sides, what do they do?
they have commutation relation, not anti-commutation relation.
They commute, right?
Yes.
Well, on the same side, they have anti-commutation relation. What this object is called in quantum mechanics? She said it.
Someone, I think,
So someone said hardcore bosons.
Hardcore
Yeah.
bosons, right? That's the issue. So to talk about a vacuum and excited state and a Fock space, you need the right statistics. Bosons are fermions. You can't have a weird thing like hardcore bosons. That's why spin systems in general are hard to solve, and they require some maquillage. Also, you could immediately have given me the answer that the model is not so simple to solve, otherwise Alex will not be standing here. You took the on it, right? It would just be, but it will be staying instead for the entire day. So there must be some issue with book. Nevertheless, there is at least a way to get the ground state of the Dicke model with a trick similar to the Bogoligo transformation, which requires not only for the ground state and the first excitations, for dynamics and more complicated fixtures in stacking, you have to do something else. Can be semi-classical methods, can be UPI. So for the ground state and for the first excited states, you can use something called Ornstein-Pevakov transformation. Have you heard about it in your life?
I'll mention it.
You will mention it. Good. Then wait and see still what you can do analytically about it. Thank you.
Yes. All right, so first let's do a brief recap of where we stopped last time, right? So yeah, we considered the Dicke model in the presence of photonic losses. And for this model, so we argued that there is a phase transition, right, associated with Z2 symmetry breaking, which is A to minus A and sigma X to minus sigma X, right, called the super radiant transition. And we try to sort of approach this problem in a simple fashion, right? So we just write down the Lindblad equations for the observables, right? So namely, I mean, in this case, for the expectation values of the spins and the quantum field, right? And and we sort of realized that, okay, so the equations for the expectation values of let's say simple observables involve 2-point correlation functions, right? And if we proceeded this way, we would have gotten for the 2-point correlation functions, 3-point correlation functions on the right hand side, and so on and so forth. And so one way to sort of truncate this infinite hierarchy is to say, well, yeah, for instance, the simplest way is to say, well, my 2-point correlation functions are simply product of 1-point correlation functions, right? In other words, that my 2-point cumulants vanish, right? And this leads to the mean field approximation, right? And for this, we have even derived the steady state, the critical coupling, and all this. And we outline that in principle, we can proceed and do something more complicated. And for instance, yeah, so truncate at the next order in the cumulant expansion and so on and so forth. But we also mentioned that this approach is a bit problematic because it is, let's say, not self-consistent, right? With like self-consistency, that we therefore expect, let's say, problems with it. And that's why we want to do, say, something else, right? So we want to develop an alternative approach. By the way, my claim is that the mean field equations, right? They're fine, right? So they're let's say they are in principle conserving, you know, kind of like self-consistent, and so on and so forth, right? Could any one of you guess like why, let's say, this mean field approximation? I mean, it's not, let's say, we don't expect it to like fail dramatically, like at later times. Whereas higher orders are, you know, we expect.
The mean field approximation, we are ignoring some high order quantum fluctuations.
Yes.
In some sense, if your dynamics is producing lots of quantum relations, you would expect to miss the point when you perform a evolution with mean field.
But also, I mean, let's maybe sort of like what I'm trying to, I guess, direct you to is the self-consistency, right? So what sort of like led to, like, let's say, the what leads to, let's say, self-consistency normally in, let's say, classical mechanics and in general, sort of like, what is, let's say, the self-consistency condition in some sense? What gives you the self-consistency?
That the correlation between the two operations will not be bigger than the correlated part.
No, I'm saying something like far more simple.
The perturbation theory will not let you to self-consistent, and it creates like circularity.
Yes.
So in this case, you have the self-consistency maybe can give you a universality of the.
I mean, okay, so let's say the simple answer is that the mean field in the language of, let's say, our like field theoretic language that we are approaching now, right? Basically, it's given by this, right? And let's say alpha or likewise sort of other fields, right? So it's based, let's say, on the extremization condition, right? And so it only so we extremize the things that, let's say, enter the equation, right? So all these sort of things that enter this equation extremize a certain object, right? Which is no longer true if you go to higher order, right? Because there, again, because sort of like there it's sort of like no longer the case, right? There is basically this perturbation. So let's say the mean field theory, right? I mean, it's extremizing your classical action, or like your classical Hamiltonian, and thereby sort of like it still has this, let's say, like nice level of self-consistency, if you wish, albeit it lacks, you know, basically like fluctuations and all this stuff, or all the good stuff that we care about. Because we want to maybe, go to higher order of correlation functions, right? So maybe we're like, okay, these observables are nice, but what about, let's say, photon number or something like this, right? Maybe we want to do this, or so, but then the cumulant expansion maybe is not the best choice in the long run. So you want to be sure that your late time dynamics is say captured without like big problems. And for this, we have a good candidate, right? So from yesterday, just the 2pi formalism, right? So, but for the 2pi formalism, we first need to go from, let's say, the Hamiltonian description to the, say, Lagrangian description or action, right? Okay. So so what's on the market, right? We have, well, let's say, so first of all, we have quantum degrees of freedom, and then we have spins, which, as Jamir, as he pointed out, are kind of funny, right? Let's say, so what do we have on the market, right? So we want to, or let's say, develop a 2pi description. So thereby we need Lagrangian of H. Right, so what's on the market? So it might seem tempting, sort of suggested to just say, okay, we have spin degrees of freedom, right? There is this so-called spin coherent state path integral formalism. Is anyone like aware of, has anyone heard of like spin coherent state path integrals? Okay, okay. So in a nutshell, right? So I'm gonna be, for simplicity, very like schematic, and also Euclidean space, single spin, all this stuff. So schematically, looks kind of like this. And so you have your spin. Then you have this thing, which is, so I mean, here I assume speed one, doesn't really matter. And then you have something like this. So this is sort of like the, let's say, the sketch, the very rough sketch of like the state coherence path integral. And let's say the problem is, you might guess, is this thing, right? So basically, so like in this form, like in this formulation, right? So you impose this constraint of like the spin length preservation, if you wish, right? So that like the spin fixed length, right? And I mean, I think, well, needless to say, it's especially out of equilibrium, it's cumbersome, right? So you may in principle say, well, I may represent this constraint via some, let's say, Lagrange multiplier as e to the power. But then, I mean, still, it's trust me, it's, not the, say, the simplest approach, right? So the resulting action then will be kind of funny. You may also say, well, but let's parameterize n simply, right? So let's pick up some nice parameterization, right? Let's say, so we have, like, let's say some Euler angles, right? Angles. So, which basically already assumes that is basically this, right? And then you would have, let's say, something like cosine theta, right? Theta and some, what's the other angle? For instance, an x would be cosine theta sine phi, right? And y would be sine theta sine phi, and z would be cosine theta. Sorry, cosine phi. Some term translation like this, but then you can imagine that, let's say you have a term like this, right? So you have sigma that, right? So in your action, it would be, so this E would be plus, or this minus omega z cosine phi, so on and so forth, right? And then, well, let's say good luck doing, let's say, a perturbation theory or something like this with the potential of this form. So it's basically like, you know, in terms of like, if you want to do like some diagrammatics, right? So this contains vertices of all, so like, say, 4-point vertex, 6-point vertex, and so on and so forth, right? So probably not, again, not the most convenient object to work with, right? So then, okay, so this, let's say, straightforward approach, maybe not the most, let's say, convenient one, right? So, but instead what we can do, I guess erase this. But then there's this idea of, well, maybe we will map our spin degrees of freedom to some other auxiliary degrees of freedom, right? Now, really, yeah, like, so what's on the market? So someone has already mentioned, yeah, Jordan Wigner map, right? I mean, so something like this. I mean, just for, say, sake of completeness. It's, yeah, it's very complicated, right? That's one thing that we already kind of like don't like. Yes. But the, let's say, far bigger problem of this map is that, as Jamir has already pointed out, is that it is it only works basically in one dimension. Right? So problems restricted to 1D. Okay. So then there was another map that also has been already mentioned, so-called Holstein, and origin person, Primakov. Which is actually quite popular, right? I mean, it is also like, so what these two maps kind of like share with each other is that they are both very nonlinear, as I like to say, right? So, okay, this part is not too nonlinear, right? It's just quadratic in this bosonic degree of freedom, but then yeah, then it involves the square root of so n minus b dagger b. So this maps it to some bosonic degrees of freedom, but in an extremely nonlinear fashion. However, right, I mean, and then yeah, we obviously but then sort of like what people often do, right?
Like square root, you mean the Taylor, let's say.
I mean, in the usual sense, in the usual sense, sort of like, you know, how you understand square roots of matrices or square roots of operators and so on. Yeah, so in the Taylor expansion set. And that's exactly what people usually do. Like, this is how people usually use this Holstein-Primakov. Because if you expand this, right, let's say, so basically, like, let's say if you say that your n is
Sorry, another triviality, the order, you assume any ordering when.
well, I mean, it's again, well, no, well, I mean, it's
You assume, I mean.
no, it's not normal ordered. It's not normal ordered from whatever. So like here, it's yeah. So for instance, it would be like, yeah. So like B dagger B, and not normal ordered from what I remember.
Okay.
But I mean, like, yes. So what people do usually, yes, is they say, well, large n, right? Pull it out, and then essentially make the sort of like 1/n expansion, and then just keep like just a couple of terms, usually just make it 1, right? And then you have, let's say, a very, I mean, far less nonlinear map, right? With very nice properties. So basically you just map your spins to bosons. But so already sort of here, right? So basically in order to like use it, it's, let's say, it's very, it's like, it almost forces you to do this like 1/n expansion, right? So that like you can't, I mean, it's really hard to use it without resorting to Taylor expanding the square root, right? So it's sort of like it forces you to do some sort of like expansion about like 1/n in 1/n, which is all right. And this is
Works so well is because you are thinking about one of the.
yes. So basically, this map, it's very widely used for semi-classical stuff.
Exactly.
So this is, let's say, a very semi-classical oriented map, I would say, which is why it's also, let's say, a very like, you know, commonly used map. However, I mean, so, you know, so again, later we will do 1/n, right? And then you might say, well, so then perfect candidate. But maybe we can find something that sort of doesn't force you to do 1/n, but allows you to do 1/n nonetheless, right? So Holstein-Primakov is useful, it's nice, but maybe we can do quote unquote better. I mean, in, you know, in some sense. So maybe we can find something, let's say, far less nonlinear, right? And you probably are, I'm not sure, like if some of you are familiar with the class of bilinear maps, right? So one of them the so-called Jordan-Schwinger map. I guess Jordan was like very yeah, productive when it, you know, when it came to like spins, right? So his name appears in 2 maps. Also with Schwinger. So yeah, so Jordan-Schwinger map, which is a bilinear map. So all right, and with okay, so Paul's polymatrices. the map is now only bilinear, and so the SU2 Casimir element, which is, yeah, like it's a fancy name for like the spin length, right? So like the spin lengths, right? SU2 Casimir element, just like sigma squared. So is M up plus 1, where M is the total Boson number. Okay, so basically, we are almost satisfied, right? Because we have a nice bilinear map, right? I mean, it may look a bit, let's say, intimidating when written, like with all these indices and so on, but I mean, it's just like a linear combination of like two flavors of bosons, like quadratic operators, right? And let's say the constraint from the from spin one half, right? That that it should map to spin one half operators, right? Now, however, relies on the fact that the total, so yeah, on the total Boson number, right? So again, for non-equilibrium, you can say, well, all right, I initiate my system such that I get the right spin one half. And then, well, we know like 2pi is conserving and all this stuff, right? So all the good stuff. So maybe it's not like the biggest concern. And I think, well, it probably is not the biggest concern, right? So there are papers that use this parameterization, you know, so I think it's all right. And they check for this constraint and everything, and so on. Seems to work. However, I think this already suggests that we can do, if you wish, even a bit more better, even a bit better. So, because here, essentially what we want is that to have a fixed, we want to have a bilinear map to something, right? For which something like this is, let's say, 1. Do you happen to know by any chance for which type of operators this condition is fulfilled, let's say, automatically?
Unitary, a unitary operator.
Well, okay, but let's say you have, let's say, a family, like you have fermions, you have bosons, right? So what kind of like, let's say, particles satisfy, like, whose like creation and annihilation operators, let's say, satisfy this condition, say by fermions, yeah, and we can sort of like do even simpler, right, by making them real, in which case we map to so-called Majorana fermions, right? So let me down. So I mean, yeah, there is a family of like different, let's say, maps to fermions, right? And one of them is the so-called Martin transformation. So Majorana fermions. And well, yeah, I mean, it's pretty much the same as, let's say, the Jordan-Schwinger.
So can you clarify just one thing for me? In the left-hand side of Jordan-Schwinger, you have it's a Pauli matrix.
It is spin one half. I'm sorry, I'm using this sort of like
Yeah, that's why I'm kind of confused, because you said that the tau SS is a Pauli matrix. Yes.
yes.
So
One you should think the sigma I like a big tensor product of many identity in all the other sides.
Yeah,
not I. And so the Pauli matrix.
Yes.
That is incorporating, if you want, the various identity in the indices I of the various fermions. And then you plug essentially the Pauli matrix where you want.
So like if you wish, yeah, so like this one is sort of like is a degree of freedom living on the lattice. And this one is just an actual, let's say, mathematical polymetric, right? So this one is actually like, the one that lives in our like Hilbert space of our like, model. And this one is just a mathematical like polymetrics, right? Which knows nothing about like the Dicke model, whatever.
No, okay, now I get it. But
Now after this Casimir elements, this one, you don't have this I anymore now. So for that. Okay.
I mean,
So maybe
I just like, I've used presentation.
this I is just the site where you apply the polymetry.
Yes.
Okay.
I mean, yeah, I was just abusing the notation a little bit. Sorry. Yes. Any more questions?
So we want this B and B1. Why it's B1?
I mean, because we want, so like, what is the spin one operator? Spin one half, sorry, operator, right? So it has to satisfy,
Okay.
basically that.
Ah.
Right, is, yeah. Or let's say, let's be more pedantic. Right? All right, so the last map that we will consider and that we will actually use in the rest of the lecture is the Matlin transformation by Majorana fermions. We have a Levi Civita symbol. Then you have Majorana beta. And I hope it's sort of like it's obvious. I mean, again, there is a summation over this thing, right? It's implied. So, and the Majorana fermions, I mean, they are so real fermions, right? So the ones for which, let's say, the Hermitian conjugate is the same as the, so like they are chargeless fermions, right? You may have encountered them in your like QFT or high energy courses or something like this. Speculations about whether, for instance, neutrinos are Majoranas or not, this stuff. But if not, you have not encountered them, this is all you need to know. For our work. Example exercise. Verify that. Like using this method, that you have the right commutation relation. And this, that this is satisfied by construction, right? So that basically this map takes care of everything, by construction, right? So you kind of like, you don't need to worry about it, right? So you have the right commutation relation, the right, let's say, spin one half constraint. It is bilinear, so it does not rely on any, let's say, so you can use it like, without any like expansion or anything, but yeah.
And you have 3 Majorana.
Yes. And you have 3 Majorans. I think there's like a whole, let's say, a rabbit hole of like some like redundancy and like, like both Majorana. We are not going there. For all purposes, This is what we need. Okay, so I think we have like 4 minutes left, and the next part is going to be already the 2PI approach, right? So the long-awaited functional stuff, functional, like the application of this functional mumbo jumbo to the actual problem. And I think we can go to a coffee break. Start here like already like with the 2PI after the coffee break, unless there are some questions. Nope, then say, sorry.
For example, if we have Hamiltonian using bosonic quantum operators, and I use one of those maps. I can find a spin system using those rules, sonic rules, that a spin system behaves.
I see what you mean. So essentially what you're saying is that, let's say, instead you have a bosonic system, or let's say Majorana system, can you always find, let's say, a system, like, can you always translate this to like a spin system, right?
For example, I can say that the spin system I found,
Yes.
the picture, behaves and has many properties of bosonic systems. Can I use these rules to try to see my spin system, fermion systems, like a boson system or
I mean, probably that's like a
because
one way of looking at this, but I mean, you also like, you realize that like the nature, I mean, couldn't care less about like our sigmas, our b's, our like etas, our anything, right? So like the Hamilton, I mean, the actual like system doesn't know about like what we like. Oh, we let's say we, instead of like now it's not a spin system, now it's a Majorana's like fermion system, right? I mean, the nature couldn't care less, right? It's just, let's say you have some let's say spectrum, right? You have some properties of your system, right? So yeah, I mean, the nature decides, right? So like, let's say if you see that, okay, it behaves like bosons and so on, then I guess the actual degrees of freedom, right? So the actual physics is bosonic in nature, right? How you sort of like then express it in terms of like whatever mathematically, it's, I mean, it's up to you, right? You can express it in terms of fermions, and then somehow like you will see that bosons emerge, right?
Yes.
But in some sense, bosons emerge because like the system is by nature sort of like bosonic, right? So the nature, I mean, it doesn't know about all this. This is just for us, for like to write equations. So I would say that, yeah, I mean, you can, again, like, let's say you find some bosonic like spectrum, right? You can say, well, yeah, but let me write down my theory in terms of, you will still see emergence of like bosons in your system, right? You cannot like cheat the nature, right? Any more questions? All right, so then we meet at 4:30.
what do you think the